Good morning, everyone. Thank you so much for being with us this morning. So I am Jean-Pascal. I'm an assistant professor here at the Department of Civil Engineering at Université Laval. I'm thrilled to be with you this morning and to be chairing this session. And there are two main reasons. So those two whys are we're going to be talking or exploring some key challenges associated with transportation infrastructure resilience for road freight transport systems. So this is the title of our session this morning. And the other reason is that it's because we have four outstanding speakers that will be talking this morning. So I'm glad that they accepted to share their expertise and unique perspective with us. So each of you guys will have 20 minutes to present, and we will probably have time for a minute or 2 minutes for questions from the audience. And of course, our speakers won't be running away afterwards. If you want to have a chat with them, feel free to connect after the session. So without further ado, our first speaker this morning is Amy Kim. She's a professor of civil engineering at UBC in Vancouver. She's going to be talking about disruptions on long-distance transportation systems due to natural hazards and other climate-related events, potential insights for freight transportation. So, Amy, the floor is all yours.
Okay, I think you can hear me. Thanks. All right, thank you very much, and thank you to the conference organizers for inviting me to speak here today on the impacts of climate change on our long-distance transportation systems. So I think I do that. Nope. There we are. Okay. So I'm going to have to do two pieces of technology here. All right, long-distance transportation systems in Canada have to traverse extremely varied and challenging terrain across huge distances to connect cities and communities and ports. And of course, it follows that the system is difficult and costly to build, operate, and maintain, even if the climate were not changing, but we know it is. And these challenges are even further exacerbated, both in the present and looking to the future. And this has really critical implications for our national economy and the health of our communities, with both so heavily reliant, of course, on efficient goods movement across these systems. All modes of the long-distance transportation system in Canada are heavily impacted by climate change. In the Northwest Territories, for example, warming trends are challenging the infrastructure and operations of airports and aviation, marine shipping, winter and ice roads, and all-weather roads. Now, decisions regarding infrastructure and operational investments are already so costly and complex in this very remote part of the world, and they're further exacerbated by major sources of major uncertainties, whether that be climate change impacts or world economic and geopolitical forces. Climate change also means that our long-distance transportations are further also threatened by natural hazards and extreme events that are increasing in both frequency as well as severity. So in BC, for example, the highway network, the provincial highway network, is impacted by many events, including extreme precipitation and flooding, landslides and snow avalanches, and wildfires. These events will cause and do cause disruptions to our transportation facilities, which range in impact from minor to catastrophic and short-term to very, very long-term, sometimes in the course of, sometimes in the range of years. Now, in BC and Northwest Territories, these transportation facilities are really the lifeline for communities as well as the natural resources economy, while in BC, the highway and rail system also connect the largest and third largest ports in this country to the rest of the country. So the question for me has been, how has climate change impacted our transportation systems in terms of how they operate and the costs of planning these systems? So now I'm going to just briefly provide an overview of the research I've done in these two places that I mentioned and discuss their relevance to goods movement. These places, the Northwest Territories and British Columbia, are very, very different contexts with very different challenges and different needs, and that's going to be reflected in the research approaches that I'll discuss. So we'll just start in the Northwest Territories, where my research group has been studying various transportation systems planning issues over the last decade. So as I mentioned before, climate change impacts every mode of transport in the Northwest Territories. It's not only the trends that come with warming, but also the increased uncertainty around what each winter or summer transport season will bring. So over the last 1.5 decades, the Mackenzie River barging system has been significantly impacted. This marine freight transportation system operates from the railhead at Hay River, just at the bottom there, across Slave Lake and then down the Mackenzie, northbound into the Beaufort Sea. This goods movement system was historically the most reliable and cheapest summer route to deliver fuel, building supplies, and other essential goods to communities along the river and to coastal communities along the Beaufort Sea. Freight moves by barge in the summer and winter roads in the winter. And if not either of these, then by air, which is extremely costly because many communities do not have all-weather road access. However, the operations have become increasingly unreliable due to changing water conditions, leading to delays, transshipment needs, and non-deliveries for the season. And speaking, in fact, to one freight company several years ago, they mentioned that many are just choosing not to send by barge any longer, and instead by more expensive trucking from the beginning, from the get-go. So some of the first work we did was to look at how water levels and thus barging capacity on the Mackenzie has changed, and then investigate strategies to better try to match the delivery schedules to fuel, contracted cargo, and other goods to the changing supply. But we moved on from this problem to focusing on how to handle the uncertainties brought on by climate change in terms of the environmental and weather conditions, given that transportation capacity seems to be dominated by this. So in essence, the open season days, the window in which sailing is allowed by the Canadian Coast Guard on the river, have gotten lower and increasingly uncertain. So what we've done is we used a financial options model showing that the expected costs in forecast years are much higher than the historical costs have been. So this led us to our next question. Do we continue with this current system knowing that there may be huge costs in bad water seasons, also combined with poor winter road seasons, short winter road seasons, or do you make big investments to build the all-weather Mackenzie Valley Highway? And if so, when does this decision need to be made, or can there be some flexibility in when this decision is made, like a wait-and-see approach? So we used a technique called real options analysis. It comes from the world of financial modeling to study the problem. And we looked at the 4 construction project phases for the Mackenzie Valley Highway identified by the government of the Northwest Territories, with results leading to the staging in the order of phase 2, then 1, then 3, and 4. And so I'll just make 2 notes about this that I think are interesting. First is that these results, they recommend flexibility. They're not saying you have to build in this year. It's more that you want to wait and see until the year's shown because conditions are going to change, and the model allows us to take that into account. And then secondly, the phasing actually follows what the GNWT did and has done for the Mackenzie Valley Highway. Around 21 kilometers of road has been constructed since 2018 as parts of phase 1 and 2, and there are no plans to build phase 4, which our results also support. And this really has to do with the enormous costs. Ultimately, what this work does is that the results of this work confirm that all-weather roads in remote areas of Canada that support both passenger and goods movement and economic development can be really difficult to justify using traditional benefit-cost analyses approaches. And so our results show that the benefits of all-weather road building may be higher than the results that you would see by these traditional benefit-cost analysis. The traditional BCA that doesn't consider uncertainties and the ability to be flexible about these decisions about when to invest. And we show that the value of uncertainty, even if in some cases it doesn't result in a positive net present value now, it may do so in the future. And just to close this, I found a recent study by the Financial Accountability Office in Ontario, which states the following. First, that costing climate impacts to public infrastructure over the long term is subject to significant uncertainty. That seems fairly obvious. And then secondly, adapting public transportation infrastructure to withstand these climate hazards will cost less than not adapting at all over the long term. All right. So that was a very, very quick encapsulation of some of the work that we've done over the last decade or so. So next we move on to BC, and we're going to look at a very different problem here, which is the problem of disruptions. So perhaps you can recall a disruption, a highway disruption that occurred near where you live or while you were traveling. And then, of course, others will have had experiences with different ones. We've had lots of experience with highway disruptions over the years, disruptions, delays, and so forth. So there are many disruptions that occur across any highway network over some period of time. But if you're in an agency like the BC Ministry of Transportation and Transit, you want a system perspective to know what is going on across the entire system, not just individual experiences, right? And they want to know this in order to make decisions to improve infrastructure resilience. And this is particularly important when these decisions are really expensive and resources, of course, are also really limited to handle what are growing problems that affect entire communities and even the national supply chain, like I mentioned earlier. However, the data to study this is scarce, very, very scarce, or of very, very low quality and coverage. So we turn to a rich and entirely open archived data source called DriveBC, which you may be familiar with. It's also called 511 in several other provinces and many states. So 511, if you don't know of it, it's a traveler information system, and the purpose is to do just that. It's to provide travelers with information about the location and nature of any problems or issues of note on the highway system so that travelers can plan their trips accordingly. So we use this data set, and so I won't drag you through the pain of the two plus years of investigating, cleaning, searching, and structuring this data for our use. It was a messy and complex procedure. But the main thing is that we were able to answer the question of whether the data could be used to answer some interesting questions about the highway system. The first here is, how long has it taken BC highway facilities to recover from disruptions due to natural hazards and extreme events? And secondly, what key factors have influenced recovery times? And to answer these questions, we used a statistical modeling approach called a hazard duration model, and I'll just briefly show you some of the main results. So we set up three classes of explanatory variables, and first, we found that highway recovery we looked at highway recovery from 4 classes of events, and we found that the avalanche category of precipitating event is fastest, recovery is fastest, while recovery from flooding events takes on average the longest, and landslides and wildfire are in the middle. So this figure on the right just shows the relative highway recovery rates in the form of a resilience triangle. So it's a well-known concept in the literature. And so what it just shows is that if, for instance, an average disruption due to avalanche recovers in a day, then it's going to take around 3 or more days to recover from the other types of precipitating event classes. Second, we looked at the type of closure and disruption. We found that events leading to full closures took longer to recover compared to those without full closures. 1.2 days for full closure for every 1 day for non-full closure disruption. This was a little different from the data analysis, from the descriptive analysis that we had, which showed that it was actually about twice as long. So somewhere from 1.2 to twice as long. Third, we found that highway disruption recovery also differs across the province depending on where you are. Very generally, that recovery takes longer as you go further north. And in fact, for here, we tested several different variables that represent this geographic influence, and broadly found that as highway density and usually population density increases, recovery is faster. When disruptions occur further north, or when air temperatures are lower, that could be further north, or in the winter versus summer, recovery also tends to be slower. And basically, this means that in parts of the province that are more remote with lower populations, recovery tends to be slower, and this makes sense because in more remote places, it'll take longer to identify a disrupted location. It will take longer to get resources from a maintenance yard to fix that disruption or to address it, and possibly there's less urgency because of the remoteness. But in terms of the major goods movement corridors like Highway 1, Coquihalla, Highway 16, recovery appears to be faster and further helped by corridor improvement projects. So this work is really a starting point to then further investigate locations with historically slow recovery. And what we want to do is we want to eventually combine this work with network hazard and criticality maps, which are being done by some states and provinces, to determine where corridors important to good movement are, as well, and then also in order to inform infrastructure decisions, investment decisions that improve infrastructure and operational resilience, and ultimately protect the major corridors that are important to our economy. So that's all I had for today. Thank you.
Thank you very much. Oh, Amy, you can stay on stage maybe. Just to make sure, does anyone have a question for Amy before she leaves?
Yeah, that's a great question. I'm really hoping that, so we're not there quite yet. So what we're hoping to do in the next sort of phase of this work is to take some of the results and look at these criticality maps, look at maps that have been made about where these hazards exist, as well as where the traffic is. So and different types of traffic. And what we aim to do is combine this information to see what it tells us about where we're seeing points of major criticality. So are there places where there is a lot of, for instance, where a major goods movement corridor where you're seeing a lot of disruptions that have occurred in the past due to maybe a certain type of precipitating event, some type of natural hazard. And so what we aim to do is eventually combine all of that, and then in order to provide more information about where resources could potentially be spent for infrastructure resilience projects, because public funds are limited, but there's so many needs across the network, and there is a real need to understand, to have more information in order to better make those resource allocation decisions.
Go ahead.
In the Northern Territories, where you are thinking about building completely new ways, are you giving input to how to build this? And because then you could build a really resilient infrastructure for 50 years, maybe, if you do it good with a high capacity.
I'm sorry. So I'm not sure what exactly.
You said that there was, or Northern Territories were thinking of going for all year ways. Are you also helping in how to design this, what properties they should have to be possible to use the next 50 or 100 years so that you get enough capacity on those roads?
Yeah, okay, thank you, yes. So for the work that I do, I look at this from a large-scale kind of planning perspective. So the types of engineering technologies and that would be used to build a more resilient system is not necessarily something that I've looked into, but that's absolutely an important point, and maybe one of the other speakers will be speaking to that. So yeah, thank you.
Thank you so much. Please help me, join me, congratulating Amy. So thank you so much. We're going to move on to our second speaker, who is Emil Tagho. Emil is Vice President of Infrastructure at the Société de Développement de la Baie James. The title of his presentation is Billy Diamond Road, a vital corridor in the heart of northern Quebec, balancing innovation, regulation, and development. So, Emil, thank you for being with us, and the floor is all yours.
Test. Thank you very much, Jean-Pascal, and good morning to everyone. If you permit me, I will take 2 minutes to say thank you to University Laval to invite me here this morning. When Jean-Pascal asked me to come here to speak about Billy Diamond's highway in the north, I was like, yes, I'm going to take a chance to tell the story of this road to all those people. But when he told me that the presentation will be in English, I was like, I won't make it. Yeah, because I'm French native, and it will probably be tough for you today to hear me. But he told me that you guys are going to be nice with me. Is that right? Yes. Great. So let us start. Billy Diamond is huge infrastructure, but before speaking about Billy Diamond's highway, I want to introduce my company, SDBG. Yeah. So our mission is to promote sustainable development in the James Bay territory by encouraging economic growth and harnessing the potential of natural resources other than hydroelectric resources overseen by Hydro-Quebec. We can do everything we want in the James Bay except hydroelectric project overseen by Hydro-Quebec. So our vision is very, very simple: to be proactive organization whose action generates significant economic spin-off for the community. So that is our goal in the life. So when I say that we can do everything we can in the north to develop, that means that we can make sure to maintain the infrastructure too in the James Bay. And we have a huge department, it's my department, who take care of the infrastructure in the north. So our territory is about 350 kilometers area and 2.4 kilometers road under our management. So we also have, oops, doesn't work. We also manage 6 northern airports. The one in orange is owned by Hydro-Quebec and managed by SDBG. That's since 2021, I think. That helps us to connect more the region with the industry and the tourism. So there is one point services which is at the kilometer 381 on Billy Diamond Highway. So it's an isolated road of 620 kilometers. This first town here, Matagami, remember Matagami, is the first town entry in the north. This is the limit here. It is the first town. We will speak more about after. And this is the only services point here. So 381 kilometers. And then you have La Grande Rivière Airport here. Yeah. So we also have dozen partnership with Cree people, and we have 4 joint venture with Cree. 2 of those joint venture is very important for us. Aguda and Niganch, which is the company that manage airport in the north. So we are very connected with the people in the territory, principally with the First Nation. So we are the government of Quebec Agency, non-budgetary organization. So if you want us to do something, you have to pay. Yeah, we have no budget coming from the government. Yeah, we are dedicated to the economic development of our intervention territory. And what is very important is that we hold the statute of mandatory of the state and signatory of the James Bay and Northern Quebec Agreement. This is very important. Yeah, let us talk about an exceptional infrastructure. I'm going to give you some technical highlight about that infrastructure. 620 kilometers, subarctic rock linking Matagami and Radisson. Ah, ça marche comme ça veut. Yeah, Matagami and Radisson. And we have 12 bridges on that road built to support a capacity of 500 tons. And one of those bridges, which is very interesting, is Ripper Bridge at kilometer 257. So the design speed is 100 kilometers per hour, which is normally used on highway in Quebec. But this road is not an highway, but because it's an isolated road, it's 100 kilometers per hour. Since 2016, we started a reflection project on that road, and till 2035, we will have invested more than $1 billion for the rehabilitation maintenance. Yeah, it's a unique case in the north, strategic infrastructure built on public lands under Quebec's Ministry of Natural Resources and Forest. So that road provides access to hydroelectric power plants. You have too many in the north. Most of the electricity in Quebec come from the James Bay. And that road provides access to all the community on the coast, on James Bay. This is a piece coming from Chisasibi, which is one of the important community in the north. And also provide access to the La Grande Rivière Airport, which is the only northern airport accessed by road in the North Quebec. And recently, we found out that Billy Diamond is very important tool for the critical access to strategic and critical mineral. This is lithium. We have 78% of lithium in Quebec are based in James Bay. So, and all the company, all the mining company that gonna explore lithium are gonna use Billy Diamond Highway. So we have some challenge on sable clay soil and glacial till, house frost throw cycle. Yeah. And you understand that because you have too many trucks, very loud, we need to maintain minimum services level while ensuring safety. It's essential to preserve this strategic asset. We also have a climatic constraint. You recently hear about forest fire in the James Bay. That was very terrible in 2023. Everything was closed. The city was closed. Yeah, we have to face that situation. And we also have increased precipitation. Sometimes we lose culverts because of the huge rain. So, how do we manage the heavy load? We have to adapt our strategy because there's no regulation to control the heavy load on BD Diamonds Highway. No legal framework historically for load limit during thaw. Road is heavily used by industrial transport, mining, and Hydro-Quebec. And to control the thaw period, we have an agreement in principle with the three main carriers for self-regulation. So, yeah, maybe before talking about the next, I'm going to show you something. This map shows you how the thaw period is managed in Quebec. You have three zones. I take the map in the transportation department, so you can find it on the website. You have zone 1, zone 2, and zone 3. Do you remember Matagami? It's the first city at the entry of James Bay. So the thaw is controlled here, zone 1, zone 2, and zone 3, limited at the entry of the James Bay in Matagami. So for the rest of the section, there is no control. So there is no possibility to know when the thaw period starts and when the thaw period finish. So for that reason, we install 6 frost gauge in 2020 to monitor the thaw period to know exactly when it starts and when it's going to finish. Thaw usually begins in April and lasts 2 weeks longer than southern zone 3. Yeah. Traffic forecast. This is, I'm going to speak a little bit about La Grande Alliance. La Grande Alliance is one of the latest agreements that Quebec has with the Cree people. And in La Grande Alliance, they have a projection in 2021 for the traffic on James Bay Road. So we are looking for more than 700 vehicles per day. That includes 40% of heavy trucks with a configuration of 45 to 115 tons. We also have an extreme configuration. This is what is actually on BD Diamond Highway. 19 to 240 tons for transporting transformers to Hydro-Quebec power plant. Those projections is based on the potential of lithium. I already told you on the James Bay. You have many projects, around 6 projects that is very active now. And we know that around 4 projects will start sooner during the 3 or 5 next year. And they're all going to use BD Diamond Highway to go to transshipment yard in Matagami. A unique regulatory statute. So BD Diamond is a multi-use road under the Sustainable Forest Development Act and its regulation. Only some article of the Highway Safety Code apply. So Article 6 and 621 concerning wave regulation does not apply. So every year you can do whatever you want. There's no limitation. But the capacity of bridges is 500 tons. But there is a regulation in Quebec for that part, so all the transporters have to ask the permit before coming on the bridge on Billy Diamond's Highway. Oops. Hybrid funding model is very special because normally there is no fund to take care of Billy Diamond Highway. So for the maintenance, the government provide fund with Hydro-Quebec because Hydro-Quebec need the Billy Diamond Highway to reach their power plant. And for the rehabilitation project, we go found some funding on federal government and provincial government. And there's also, we use also Quebec's infrastructure plan so we have to ask every time. There's no room to go take funding to take care of the Billy Diamond highways. We have to go look after money every year. Strategic corridor for northern Canada. Yeah, this map is very interesting. Do you remember when I told you about La Grande Alliance? Yeah, there is two huge projects coming. I don't know when, but the study is already done. So in La Grande Alliance, we are looking to build a deep water port project in Ouatmagospouy and to extend Billy Diamond Highway from Radisson here to Ouatmagospouy. Transship is here, transship yard is here, so all the truck coming from the mine will take Billy Diamond Highway to come from the transship yard in Matagami. Yeah, this is kind of a big plan to see how it works in transportation in the north and what is potentially coming in the future. So for the regional integration, the Billy Diamond connects 9 communities and several industrial hubs, La Grande Alliance, as I say. To finish today, autonomous vehicles testing opportunity on Billy Diamond's Highway. Why? It is a possibility. There is low traffic, ideal test environment, long linear road, few intersection, extreme condition, a northern corridor for smart transport innovation. So we are open to for any test that the industry of transportation want to do. So thank you very much. That was a little bit tough.
Thank you so much, Emil. I think you are being very hard on yourself. It was fine. It was all good. It was very interesting. Thank you so much for this talk. Does anyone have a question for Emil? We have a little bit of time.
I would have plenty, but I will just make one. And before that, Emil, you are almost among friends because most of us, English is not our first language. Okay, mine is Spanish to start with. Okay, so very, very interesting. And again, like with Amy, it resonates a lot with what I do. So one question that I have is, you've put the corridors there and you've shown how difficult it is. How are you planning, or how do you do with mixed traffic? Because one of these, I mean, you have the trucks, but you also have, the trucks with professional drivers, and you have also cars or pickups with people that have to go to the mining companies, contractors that go, and how are the speeds? How do you deal with the speed limits of this mixing traffic? Because a lot of the accidents that we have are about that.
Yeah, that is a good question. And the point is that on Billy Diamond Highway, there's not a huge traffic, first of all. But for the mining project coming, there is an environmental committee that has to give their authorization to all the mining to start their project. And one thing is very important that the environmental committee asks to them is to have an agreement with SWG, with us. And what we ask to them is to show us their plan of transportation. We have to make sure that the speed is under control. The road is designed for 100 kilometers per hour, but we won't allow a huge truck, very load, more than 70 tons of material to have a speed like 100 kilometers per hour. So we have a certain control on that point. But in La Grande Alliance, there is a study that has been done, and the result is that we're gonna build a new lane for the trucks. There is a possibility to just create the passing lane, to make sure that people are safe on the road.
Another question, maybe? We have time for one last question.
No more question?
Oh,
Yay.
don't run away. I will ask you one, Emil. Emil, I have a question for you.
Okay.
A very short one, but can you just, I knew you were short on time, but can you explain to us very briefly what was the context of the construction of that major infrastructure back in the 70s, I guess?
1970.
How much time did it take to build it? Why was it built in the beginning?
Yeah, for sure. The road has been built during the year 1917 for the electrical project in the North Quebec with Hydro-Québec. So it was to provide the access for the power plant to building. So the road has been built in 450 days for $450 million. So that is very special. And they have to build the road in a faster time. And to do that, they put huge boulders inside the infrastructure. So when we started rehabilitation project in 2017, we found out that there were some pattern on the road that was not normal. And when we opened the infrastructure, we found out there were too many boulders. So at that point, we understand why it was possible to build 6 and 20 kilometers in 440 days.
I have a question as well.
Yeah,
Because I see that it's a Volvo in front here. So then I wonder, do you have, does everybody that drive in the north have satellite connection to the trucks and cars, or how is how would autonomous, is there full Wi-Fi coverage, or how is it? I'm just thinking, satellite. If you should drive autonomous, you need to have full, you have to have contact all the time with the central computer somewhere in the world.
C'est quoi le type de connexion qu'il y a sur les véhicules satellites? Est-ce qu'ils se parlent par radio? Comment que les véhicules communiquent entre eux?
Oh, that was a good question. Sorry. Yeah, they have radio in their trucks, and our company also connect our people on the road, because we have inspector on the road. They just drive on the road to see if everything is good on the road. They also have a radio in the car they can communicate, and they have a satellite too. And from now, there is a possibility with iPhone 14 and more to connect to the satellite, so you can text on Billy Diamond's highway. And recently, EU communication company started to install the tower, the communication tower. So in a very short time, during the next 2-3 years, the whole road will be connected.
Thank you so much, Emil.
Thank you, Jean-Pascal.
We will move on to our third speaker this morning, Professor Guy Doré, who is an emeritus professor at the Department of Civil Engineering of Laval University. He will be talking about navigating the challenges of heavy vehicle transportation on resource roads. So please help me welcome Professor Doré.
Well, thank you very much, Jean-Pascal, and the conference organizer for inviting me. I'm really pleased to be here today. As I was rehearsing my presentation, I thought my title was perhaps a little bit misleading. I said the challenge of heavy vehicle transportation, it's going to be more the challenge of resource road management than the heavy vehicle circulation, but given the heavy vehicle circulation. So that's an overview of the challenge that we experience in the north for resource access roads. So resource access roads, they essentially build to provide access to natural resource, like hydroelectricity. We just saw a very good example of that with the Billy Diamond Road, lumber, forest, mineral resource. It's also used to access communities in the north and the land also for fishermen and other people interested in wildlife. It's often considered as a necessary evil by the industry. It's very expensive to build and to maintain and does not generate any revenue, but they need it. So and generally it's pretty far from their core business and their expertise. So it's necessary, but it's not their preferred subject of discussion, let's say. Resource access roads are long linear road structure crossing a wide variety of landscape and environments and physical environments. So that's one of the difficulty with resource access road. They're a simple structure, typically just a few layers of gravel laid directly on the ground, and they're generally unpaved, though some main artery are paved, like the Billy Diamond Road. And these roads are in complex interaction with their physical environment, the landscape and the soils, and also the climate. So characteristic of low-volume road, no, not low-volume road, but resource access road, it's they do have typically very low volume of traffic, but vehicle can be very heavy. Okay, so that's a difficulty when you're doing the design of something like that, because generally you consider the number of load that's going to be applied on the road when you do the design. Climatic factor are a major factor in the performance of these roads. The deterioration modes and also the serviceability level or tolerance we have for different type of distresses vary considerably from these roads compared to normal highways. And there's lots of constraints affecting construction, maintenance, and access of these resources. So availability of equipment, expertise, the remoteness is a huge challenge. availability, budget, etc. So the main challenge when you're building road, they're not the only challenge, but there's some of the main challenge. You need to fully understand the characteristic and the physical and climate environment of your road. You need to design embankments and pavements to provide adequate bearing capacity given generally low volume of traffic and uniform performance along the road. You need to find good quality aggregate, organize extraction and transportation for the road construction. You need to organize construction logistic, and in some cases it's really a major challenge. And then you need to maintain that road to optimize its operational capacity. So looking at each one of these challenges, so the understanding the physical and climate environment of your road is, of course, to start with, is a key factor. The road, again, are long linear structure, and by definition, they'll cross all sorts of type of soil, climate, and environments. So you can go from like a forested, lowland, moist soil to high land with taiga type of forest, low and in relatively dry conditions. So it varies along the road. Of course, different type of soils. The operational capacity of the road will be essentially limited to the weak links of the road. So will be limited by the weak links of the road. So any sensitive area along the road will dictate the capacity of the road. So among the sensitive sensitive area that we can have along a road, we can consider like the compressive soils, like clay and peat. We can now also consider water-sensitive soil, soil that are very sensitive to variation in moisture content, frost-sensitive soil, and permafrost. You have to keep in mind that most resources currently that are attractive and people would like to access those resources are in the north, and 50% of the land area of Canada is actually characterized by the presence of permafrost. So permafrost now is like a major concern when you're building, like for example, the extension of the Beasley Diamond Road will be in permafrost area, so this has to be considered. So, of course, one of the key aspects is you need to have good geotechnical information on the road corridor. So, looking at each one of these type of problem, like compressive soil, you can have peats and clays that are compressive, and they're very widespread in the north. So it's a common problem to have these compressible soils. Significant settlement are to be expected in those conditions, and you need to manage the consolidation of those soils. So you need to manage the drainage of water, because like consolidation involves expulsion of poor water. So you need to drain that water. You need to be also to manage the pore pressure inside the soil, which can lead to instability. You also need to consider the time for the consolidation process. So if you're in fine-grained soil like clay, it's going to take very long periods, that can be a year and even more, to fully consolidate the soil. So in the meantime, you're going to have, again, to manage settlement and movement of the road. In order to mitigate those problems, for clays, again, the basic principle is to force consolidation of the clays prior to operate the road. So you can do that using surcharge or other technique. You can also use reinforcements at the base of the embankment to help stabilize the embankment. Or you could use lightweight material, like for instance, if you're in a forestry harvesting area, you could use wood chip as an embankment material to minimize settlement. For peat, excavation is an option if the deposit is thin and if you're not in permafrost environment, because the peat is a very extremely important protective layer for permafrost, so you don't want to remove it. But in seasonal frost area, if the layer is thin, you should remove it. If it's thick, then you should consider consolidation with or without reinforcement at the base of the embankment. And also another option is to displace peat using a special construction method to force the peat to move laterally and reach the mineral soil underneath. Water-sensitive soil is also an important problem when you have fine-grained soil. It can cause significant problem during the construction and the operation of the road, and the problem is strongly exacerbated during thawing period, whether you're in seasonal frost or in permafrost condition. If soil is thawing, you're going to have excess water and lots of problem with bearing capacity. The solution to that, or some of the key solution is to use good quality material first. So good gravel, free draining gravel for the pavement and also the embankment. Good preparation and the preparation of the subgrade soil. So compaction and make sure that the surface of the soil drains freely towards the ditch. Adequate drainage to remove water away from the platform. And then you can also use drainage composite, and chemical stabilization is another option to reduce the sensitivity to water, to moisture. Frost-sensitive soil problem that's associated with water sensitivity of the soil. In Canada, most of the roads in Canada are affected to different degree to frost action. The problem can cause heave and distortion of the surface of the road, can be significant problem for, again, winter operation of the road, can cause crack to the surface, and it was also cause significant bearing capacity loss during spring thaw. And this problem is likely to affect the functional and the structural capacity of the road during its operation. Some solution to the problem, of course, use good quality material for the embankment, for the pavement itself. Use thick foundation to reduce the thickness of the soil that's going to be affected by frost action. Insulation can be used in severe cases to reduce frost penetration, then frost action, by the way, and drainage also can be used. And another widely used technique to reduce problem during spring thaw is to use load bands during the spring to reduce the problem associated with loss of bearing capacity. Construction in permafrost condition, again, as I said, it's a widespread problem in the north of Canada. Permafrost is perennially frozen ground, soil. It's a physical environment that's in a very fragile equilibrium with the environment, and mainly with climate. So it will be stable if climate is stable, if nothing happened. The picture on the right shows a cut in permafrost soil, an exposure that was created by a landslide. And you can see there ice wedges near the top. These are massive ice structure in the ground. I won't go into the detail of formation of ice wedges, but these are significant, again, massive ice structure in the ground. And if you look just below the icicle, you see ice lenses. And as a matter of fact, that soil has somewhere between 60 to 70% of content of ice. So as long as this is frozen, this is stable. But if it warms up, the property will change quite drastically. And if it thaws, it really can cause some severe problem. So then, of course, the soil becomes extremely unstable, and that problem can be caused by site disturbance. If you're building something on top, you'll disturb the surface and you'll change the equilibrium, and that can cause severe problem. And it can also be caused by climate change, which is happening at a very fast rate in the north. So you see a picture of a ground surface in northern Yukon. It seems to be a very nice place to build a road. You can see that it's gravelly, probably glacial till, flat surface, no obstacle, perfect place to build a road. But if you look underneath, there's several meters of ice, just a few centimeters below the surface. And if you don't know that, and you disturb, like the kind of thing that you see there, a thaw slump can occur and just carry your road away. So this can be extremely unstable and dangerous. So that's this buried massive ice. Ice wedge, I just talked about the ice wedges, and they're widespread in the north. Again, massive ice structure in the ground. You can see that at the surface. Now, at least you have an indication that there's ice wedge there. And you can see the trough going across the road and the slight depression in the road. And if you're not careful about those things, that kind of thing can happen. So actually, the road can collapse locally because of a thawing of an ice wedge. Thaw settlement, different thaw settlement. Differential thaw settlement is a very common problem everywhere in the north where permafrost exists. And again, that's a management nightmare. Embankment stability, problem with thaw slumps. In that case, that's the Dempster Highway in northern Yukon. Actually, it's in the Northwest Territory. And you can see on that road, there's two thaw slumps on the left, one in natural ground, and one that's started from the embankment going toward the little creek there that was filled by the maintenance crew there. There's two more forming on the right side of the road, two thaw slumps. And again, this requires very frequent maintenance and very close monitoring to make sure that there's not the road's not carried away by these problems. And if you're standing here and looking towards the north, a few hundred meters, there's a major thaw slumps. That's in natural ground. It's caused by natural reason, by climate warming. But the flow is actually moving towards the highway and is now about 100 meters from the highway. So in a few years, the flow will probably affect directly the highway. And again, you see in that thaw slump that there's several meters thick of pure ice underneath the surface. So in the case of permafrost, you really need very good quality geotechnical information to make sure that if there's to verify the existence of sensitive permafrost and also delineate the sensitive area. You need also thermal and mechanical design. And the difference in what we do usually for roads is the thermal design. Like, we're not used to work to do thermal design when we do engineering. And in permafrost area, that's a must. You need to do thermal design. And in some case, thermal stabilization and mechanical stabilization will be required. You see two examples here of thermal stabilization using thermal siphons in the bottom and heat drain at the top. The design of embankment, again, well, you want to ensure adequate performance considering very heavy traffic. Again, we're dealing with a structure of using several layers of gravel. Currently, the design methods for low volume road, that includes resource access road, are essentially empirical, okay? And in some cases, just rule of thumb. So there's not much technology involved in pavement design for resource access road. The current trend now is to use mechanistic empirical technique where you calculate stresses and strain and compare that to allowable values. So pavement design, like the problem is when you're doing the pavement design, you use the factor N, which is the number of load application expected during the lifetime of the road. And that value is very low for resource access road. So you have to account for, this will typically lead to minimum thickness. But you need also to account for extreme loading condition, and you should consider also limit state analysis of your system. Accessing material very quickly, difficult to find good quality material in the north, and when you find it, it's sometimes very difficult to access. Like there's an esker on the picture on the right, but it's very difficult to get there to actually extract the material. So, and you need some minimum quality. Ideally, it should follow that band, very narrow band, gradation band. And if it's too fine, it's going to be either unstable, slippery, or dusty. If it's too coarse, it's going to be unstable. So that's a challenge. So, of course, you have to find the deposit, you have to extract the mineral, and you also have to transport the material and treat it to be usable. Construction logistics, very complicated in the north, especially if you're not connected to a road network. If you're at the end of the road network, like for instance, the Billy Diamond Road is connected to the road network, so relatively easy to mobilize equipment, but if you're not, it becomes extremely difficult. I have to consider winter construction versus summer construction. Both have advantages. Winter construction allows you to travel easily on the surface, but the condition can be pretty bad. In the summer, it's difficult to work, but it's relatively easy to actually do earthwork. Maintenance, optimization, you have to act at the right place at the right time, and Jean-Pascal is getting at the front of his seat, so I guess I need to hurry up. So the key is, again, to act at the right time, at the right place. Different type of maintenance and rehabilitation that can be applied in the north. Maintenance management, important. You need to develop a capacity to react considering the anticipated problem. So if you're expecting, for instance, erosion by water, you need to stock coarse material, crushed rock, to eventually be able to come and stabilize the erosion. Optimize the resource strategically, promote sustainable intervention, and plan upgrade the place where recurring problem happen. In conclusion, the resource access road, it's a major asset essential to access the natural resource. Yes, it's a necessary evil, but since it's necessary, might as well do it right so it lasts long and it's relatively cost effective. And currently, for design, construction, and management of the road, we very often use low-end technology, and there's a need to improve that and actually do more research on on resource access road and use more higher-end technology. With that being said, I'd like to thank you very much for your attention. I'm sorry if I used too much time.
All fine.
No time for question. Huh?
Always time for at least one question. We can make it. Doesn't one? I have a question for Guy. It's going to have to be a short one because we are short on time, but we can certainly make time for one. Over there.
Oh, okay. I have a hard time. Yeah. Okay.
Sorry, thank you very much. It was a great presentation. Can you just give us a bit more insight into how the permafrost is changing with the warming climate?
Well, again, as I mentioned, it's a very fragile equilibrium, and any change you do at the surface will affect the equilibrium. So you have to be smart on what changes you're going to be imposing, because if you build an embankment, you're changing the surface. So if you, for instance, remove the peat layer, you remove a protection layer. You replace it by gravel. So you have to calculate the amount of gravel needed to do the same protection, to achieve the same protection. So if you don't do that kind of thing and force the material, the soil to thaw or induce thawing in the soil, if you have sensitive permafrost, meaning more than 20-25% water content in the ground, then you probably have excess ice in the ground, more than the pore the soil can stand. So you will have a very unconsolidated soil when it thaws, very unstable. And in many cases, you have zero shear resistance when the material thaws. That's why you see the material flowing, because it becomes liquid. So it becomes extremely difficult to manage when you induce that kind of problem. So, yeah, so that's a very short. Yes, changing very rapidly. First of all, the northern part of Canada and most of circumpolar area are the place where the climate is warming the fastest. It's warming 2 or 3 times faster than in southern Canada, for example. So, of course, permafrost is warming, and it's also degrading. So this is happening without any man-made disturbance. If you do the disturbance on top of that, then you're amplifying by far the problem. So, yeah.
Thank you so much. So we'll move on to our next speaker, but thank you so much, Guy. Our fourth speaker is Catherine Lawson. She's a professor at the Department of Geography, Planning and Sustainability at the University of Albany. Please join me to welcome Catherine. Thank you so much for being with us.
Thank you. Well, I'm going old school. Got to stay close to these mics. Brought my paper. So we'll get underway. So I'd like to also thank the Planning Committee and especially Jonathan for giving me this opportunity, and to my fellow speakers. And we'll circle back around about the important things that you have already said that we want to talk about today. So yes, there are rough roads ahead, and yes, I did use AI to make these graphics for us. But let's get started. And I think I just have to hit this. What do I have to hit? Very good. Excellent. All right. So, a little bit of background, and these are things that we've been hearing. There's continued growth of truck-dependent industries and households that depend on deliveries. There's an acceleration of extreme weather and other natural hazard events. There's aging infrastructure under additional environmental stress. We just heard about that, including bridges that are experiencing scouring with more frequent flooding events. And so that leads us to the question, how can freight planners prepare for growing natural hazard risks while increasing their capacity to respond and demonstrate resilience? And especially this is true for the challenges of trucks. And here's a couple of the reasons why. So in the transportation planning community, it's been a tradition that we focus on the average good day, which means that a lot of that data about bad things happening, outliers off the table, is not getting included in traditional analysis. And then we have this situation with extreme response community plans. Yes, they're good when the disaster strikes, but they often happen without input from the freight community planners and members of the freight community. There's also a lack of strategies for anticipating the potential risks in a dynamic environment for trucks, and a lack of data products configured for the appropriate geography and the conditions where trucks travel. That's probably my most important message, and we heard it earlier. It's the data, folks. All right, but in order to understand what data you need, it's really great to have a good framework, and we have one that I recommend. This is the Risk and Resilience Framework Jonathan and his colleagues worked on. Has 3 parts. It's got infrastructure resilience, which are the routes, adaptations, and the reduced time to return to normal operations, so that getting back to business is really important. The user resilience is being prepared for change while remaining profitable and having the capacity to recover from losses. And very important is the organizational resilience. And this is preparing for future events with recovery strategies, increasing your response times, and responding with strategies to maintain operations. So we want to keep this in mind. We're finding that there's a lot of attention to the infrastructure. AASHTO in the United States has been adding a user resilience idea, but the organizational resilience is where we really need some help. So the state of the practice in the United States got underway in the Biden administration when on May 5th of 2022, the Department of Transportation made the proclamation that there was going to be a new requirement for state departments of transportation to include extreme weather and resilience as part of their life cycle planning and their risk management analysis within their state management plan. In these state management plans, most of them we think of as the Transportation Asset Management Plan, the TAMP, is where some of this information started to grow. But unfortunately, after reviewing the 50 plans that were submitted, they were really soft. They were policy language. There was little data-centric approaches that give you the scores of the metrics so that you can get down to business on those segments of the road that need attention. Now, we did have a few outstanding states. One of them is Utah. And so the Utah Department of Transportation, they said, well, let's put together some seriousness here. So they looked at their assets. They looked at a set of threats, and these are, they've got flooding and they've got earthquake, but they've also got some unique ones, which are their debris flows. They put together a user cost construct. They looked at their risk of value by monetizing their risk. And then they looked at criticality. We heard a little bit about criticality before. And then they looked at their additional risk story till they get to the return on investment. So where are the trucks? Well, we got a little bit of truck here. This is the ratio of the AADT over the truck ADT. But is that sufficient for what trucks need in the way of risk and resilience? So they set about working on their approach, and they're using the ArcGIS to develop these scores for their criticality and their exposure. And they're putting it all together in a story map format. So here's an example. This is a story map looking at their different identified hazards. So red being the worst, we're looking at earthquake difficulties. So this seems like a good way forward, and it's available on the web in their risk prioritization analysis. But I was looking for the trucks. And when I got to the truck AADT and it looked like we're gonna have some weighted criticality results, the work is still in progress. So we don't have an answer there as to what states will be able to do. And again, each state is taking their own approach. There is no uniformity yet as to how to do this. So here we have Iowa. They took a different approach. They looked at some different factors. They do have criticality in it though. And they have trucks, but it's just truck AADT. So when we think about all the things we've been hearing here at this conference, that seems like a pretty limited way of understanding trucks, risk and resilience. So let's look at some folks that are actually looking at trucks. This is a piece of truck-focused research, and in this, they looked at truck GPS. These were raw GPS traces, and they combined that with a flood model, and they developed something that we can measure. So the first thing is the functional resilience, which is the rate of travel time index ratio before the flood event, and then comparing that to after the flood event. So that at least gives you some comparative analysis. And they added to that a topological resilience, which is the ratio of the most connected road segments in the network divided by the total number of road segments in the network before and after the flood. But that's still not enough. So let's see, what are these challenges to our framework? So the first challenge is that trucks, for the most part, we're thinking about trucks that are running interstate trips, and they're going to require a harmonized network that crosses jurisdictional boundaries. And we saw jurisdictional boundaries in Europe as well. And then we need a conflation technique that will append the state-specific road attributes. So each state has its own way of laying out their geographic information systems. So I have an applied data science team, the Albany Visualization and Informatics Lab, AVAIL, and so we've been helping New York State DOT set up a platform that will allow them to conflate all of their valuable but very unique information. The recommendation here is that everybody should think about using OpenStreetMaps as a universal base map, which we can then use these conflation conventions. This gives us real power when it comes to moving data and doing analysis across large networks. So what about the challenges for the users? Well, here's where I'm going to say that actually commodities matter is what you're hauling. And when you go to a truck weather conference, there's always somebody who's going to talk about that van that was traveling, didn't use a climate-controlled van. They were carrying beer. It suddenly got very cold. All the beer got ruined. So that means we need to pay attention to what's happening with the hazard and what is happening too. So we have in the United States, we have the commodity flow survey, but the geography is much too large. We do have traditional roadside surveys, for example, the one that was done in Washington State, the Intercept survey. Here in Canada, the Trucking Commodity Origin and Destination Survey. And then we have TransSearch and the Freight Analysis Framework. However, they are model data, so we have to be careful about their assumptions. We do have a new data product on the block called GeoTab, and I think they just changed their name to Altitude. These are truck traces that have where the truck started, where the truck ended their trip, and what they're carrying. So we think that this is going to be very beneficial for understanding the relationship between what you're carrying and what's going to happen. But we need a typology of commodities with respect to natural hazard event impact, because not all things that trucks are carrying are going to have the same level of risk and could have different outcomes. And then, again, importantly, what about the organizations? So it turns out that there have been inconsistencies in the historical natural hazard event data. NOAA has a storm event database that most people use, and FEMA has a damage database that a lot of people use, and they don't align. And so if you do an analysis with one of these, you'll get a different answer if you do the same analysis with the other one. Not a good situation. So FEMA provided funding through the relationship I have as a cooperative technical partner with my data team, and we have just last week launched the framework for unifying sources of information on natural disasters, also called Fusion. And if my friend back there will click on the hazard data link, we'll take a look at it real quick, and we'll scroll through here. So what this has done is it's fused together with all the recipes about how to do it, the two data sets, and then created some data products, including that product right there, which is the ability to search by county. Not only that, but you can download that data by county. Okay, so now we can go back to our regular show. And so what that means, if I can get this to trigger, come on, there we go. That not only do we have that data that's now become available, but we also have some situations with the earthquake zones. One of them is the New Madrid, called the New Madrid, and it includes 7 states along the Mississippi. To my knowledge, they are not working on this at this point, but there's also the Cascadia subduction zone, which goes from Canada through Washington down to Oregon along the I-5 corridor. They have been doing some analysis on this, but not enough to get us into a good place for when that big 9.0 hits. So what we need are county-level hazard data for multi-jurisdictional truck routes. Well, so what I'm talking about is like a jigsaw puzzle, taking the county data, putting it together along the routes where we know these trucks are running. But in addition, it makes a difference about the natural hazard impacts by the configuration of your truck and the weight of your truck. We heard about weights yesterday. And what it means is that wind speeds have a different effect on an empty truck than on a full truck. And when it's really raining, it matters how much it rained yesterday, how much it's raining now, and how much more it's going to rain, and on what kind of terrain that rain is falling. So we need a set of composite weather observation terrain types, because that place matters, to produce the conditions of concern for trucks by road segment. So now my challenge for you, the research community. Pulling together what we know is happening and how we can start working towards a more resilient set of data in the future. Our data sources are somewhat at risk, and maybe more at risk than we know. So let's think about this. What if we used our new electric and autonomous vehicles as natural hazard probes? How do we do that? Well, we're building these units because we just are working on building them now. How about installing a low-cost onboard automatic weather station? And if you're going to be traveling in an area where we know there's going to be earthquake activity, have some earthquake detection centers, and then use this information through the transmission of real-time ground truth observations in a new form of computing called fog computing. And this would allow us to have natural hazard alert system for the fleet managers, for the multi-jurisdictional organizations, and for us, the researchers, to improve the segment level conditions and positions for the R&R plans. And the importance of this, I can't stress enough. We have thought about computing with central computing. So this is like NOAA, give us your weather observations, we'll send it to the headquarters, and then they'll send you back what that means. We have edge computing, which I originally thought was going to be useful with putting the weather stations on the vehicles and have the computations happen in real time on the vehicle. Turns out we're learning in the maritime world that's not the best idea. And distributed computing means that you have static locations for those communications. In fog computing, it's extremely agile, and so wherever in the maritime, wherever you have a lighthouse, wherever you have a barge, wherever you have a place where the data can be sent, the data can be collected, the data can be processed, the alert can be manufactured and can be sent back to who needs to hear it. And I'm thinking, yes, you need to hear it if you're one of those trucks, the autonomous trucks that's not supposed to be running when there's heavy snow. So if we have a playbook, here's what we could do. We could have natural hazard events by county along the truck routes. We could have the road network analysis using the truck volumes and the road segment details. We'd have the commodities of concern and truck configurations. We could make sure we had the management response assets in place through ITS and through the communication apps. We could have coordination upstream and downstream. And maybe we can have fog computing alert systems that can improve the accuracy of the event details. And so this is a real picture. Really bad things are happening, so the sooner we can get down to business, the better. And thanks so much.
Any questions for Catherine? We have a question in the back.
Catherine, that was fascinating. Thank you very much. Seems to me that we are going into a situation like a war, really. You know, in the Second World War, the British mapped all industrial facilities, and they knew where everything was being made, so that when things got bombed, they could move production somewhere else. So it was all about planning for events. To me, it seems that the equivalent now should be some models which can understand what's going on and can predict what happens when a particular area floods or whatever, how you reroute, how you shift things from one place to another in order to keep the economy moving. So is that another part of what you've, I mean, this is the data that you need, but I feel that there's a need for a model which assembles it all together and is able to then be predictive about what you should do.
Yes, we're working on that, and my team wanted me to bring it with me, but it's not quite ready yet. But what that includes is the segment-specific problem, so and including all the things underneath the road. So what's happening in Canada is really important. And then getting the data to do the criticality, the betweenness, and there's a whole bunch of algorithms about this, but you figure out where the problem place is, and then what are the alternatives, the detours, and how long do they take, and can you run a truck on those roads? So we do have enough data at this point to do that kind of modeling, but unless we use OpenStreetMap as the bottom base map so that we can connect up everywhere. So we have to get out of this is my data, I've always used it, to, yes, that's your data, but we're going to connect it to this open street so it can speak with everything else. But the ability to respond and to get the emergency preparedness community to help us know where they need to go when something happens. So the FEMA doesn't do transportation, but they are allowed to do a little bit of commercial transportation, which I think is mostly the logistics for getting things prepared before the storm and then rushing in there with the trucks. But because DOT has not been in the hazard business, FEMA has, but there's this huge gap. So things that we learned on the FEMA side for how to deal with it, we want to transport those over to transportation So these new models will be multidisciplinary, but it's very feasible. And if Paul finishes running by model, we'll have some results for you very soon.
So I suggest we end the session here because we're a bit late, but we started actually 5 to 6 minutes late. So we did it on time, but we started late. So sorry about that. Thank you so much, Catherine, for your presentation.
Thank you.